Okay, year 10 physics. So today we're going to be looking at the next topic in electromagnetism, and this topic is called, well, it's called electromagnetic induction, but it's also known as the generator effect because this is how we generate electricity. This is how we get electricity that you're using to power your computers and air conditioners and lights and fridges and everything at home right now. So this is all by the generator effect, and that is what we're looking at. So let's get started here. So the generator effect, as I mentioned, also known as electromagnetic induction. So those two things mean the same thing. So in order to generate electricity using this generator effect, essentially three things are needed. We need magnets, we need wire, and we need some movement. And you can see in this picture right here that the movement is being caused by a wind turbine, but that movement can really be caused by anything. It could be caused by your own arm turning a generator or a turbine yourself. So let me just move over to the pen tool here. Okay, so those are the three things required to generate electricity. You need magnets, you need some wire, you actually need a complete circuit, and you also need some movement. So let's see how this works. Okay, so zooming out a little more, whoops. So the generator effect is when mechanical energy, that just means like physically moving something, so is when movement is transformed into electricity. So we're using mechanical energy, which is just something moving, and we're turning that into electricity, which is electricity. So this is also called electromagnetic induction because it involves a current being induced. So we're causing a current to happen by moving a wire in a magnetic field. Okay, and so again, this is exactly how all of our electricity gets to our homes. This is all created by electromagnetic induction, or also known as the generator effect. So here is the basics of what is going on in the generator effect. Here is what is needed. So we can see right here, it says, if a wire cuts across magnetic field lines, it causes electrons to move in the wire. So right here, we can see this thing is a piece of wire, and we can see that there is something that is pushing this wire down this way. So this wire has to be being pushed downward. And as this wire is being pushed downwards, you can see that we have all of these field lines that are going across this way. You can see that as this wire gets pushed downwards, it is going to be cutting across all of these field lines. It's going to be cutting through the field lines as it moves down. And that is essentially what is needed to generate electricity. You have to have a conductor, which is cutting. We use the term cutting field lines. So when this piece of wire is being pushed downwards, we can say that it is cutting through all of these field lines. Okay, and when that happens, basically, when this piece of wire is pushed down and it cuts across these field lines, what that causes is the electrons inside of the wire are getting a push. So they're all getting a push the same way. Let's just assume that push is in this direction right now. So as this wire gets pushed downwards, all the electrons in it will receive a push, either, in this case, it's either left or right, but actually in this case, it would be to the right. It would be to this side. So that the result of the wire cutting the field lines is electrons getting pushed to one side. And we all know that electrons moving, well, that's electrical current. That's a current. So we've just created electricity by pushing this wire downward and cutting across these field lines. Now, all the electrons in the wire are going to start moving in the same direction, and essentially that's an electric current. But really, it's the EMF, it's the voltage or EMF that causes a current. Remember, you can't have a current without a voltage. So really what's happening here is that there's we say there's an EMF induced here. And we'd say, let's just say this side of the wire becomes positive and this side of the wire becomes negative. And so the current is going to flow from positive to negative. Okay, so now if we do the same thing and this wire is part of a complete circuit, then we get a current. So last time I was just showing the piece of wire. Now here we can see there's a whole circuit. So if we move this wire downward like this, so if we apply a force and move this wire downward this way, we can see that we have electricity now flowing around our wire, and it's going to light up this light. So when that conductor, the piece of wire, is part of a complete circuit, we can get a current to flow. So what do you think would happen if we if we pushed the wire down through this, cutting these field lines, if we pushed it down this way? What if we push it even faster? So faster than we did the last time. So the thing to realize is the faster you move this down, the bigger the current produced is going to be, because the bigger the EMF is going to be induced. Okay, so now what do you think would happen if instead of pushing the wire downwards, now this time we're pulling the wire upwards? So we're pulling this wire upwards. Now the only difference is, you can see if I scroll back to this picture, you can see here the current is flowing counterclockwise when the movement is downwards. But if the movement is upwards, now we can see that the current has reversed. Now the current is flowing clockwise. So you can see the direction that the wire is cutting the field lines makes a difference. So again, if that piece of wire was not a part of a complete circuit, if it was just a small piece of wire, we would still get a voltage across here. We would still have a voltage across the wire. One side would be positive, the other side would be negative, but we wouldn't have any current flowing because we don't have a complete circuit. So no complete circuit, no current flows, but you still do have this EMF or this voltage across the wire between this end and this end. And also, as mentioned down here, it does not matter whether you move the wire or you move the magnet, the result is the same. The thing is, we could move this wire downwards, or we could just take this magnet and we could move the magnets upwards. It doesn't matter, it's the same thing. It's just the relative movement between the two that is important here. So now the thing is, how can we know, like if we go back up to this picture, how do we know that if we move this wire upwards, how do we know that it's going to cause clockwise movement or a clockwise movement of the current? How can we know what direction the current is going to go? Well, there's a rule for that. And here is that rule. Okay, it's called the right-hand rule. And this is how it goes. So if you point your fingers in the direction, so you have many fingers, right? 1, 2, 3, 4. There's many magnetic field lines. So that's the way to remember. You have lots of fingers. There's lots of field lines. So you point your fingers in the direction that the field lines are going. And then you point your thumb in the direction that the wire is moving. And then the palm of your hand shows you the direction that the current will flow. It shows you the direction of the induced current. Now, I know this sounds kind of complicated without seeing an example, so let's look at an example of this. Okay, so here we go. We have this piece of wire, and we're moving it, so we can see that the force on this wire is this way. So we're pulling it this way through these field lines. So how do we know which way the current is going to go? Well, in this case, we would have to use our right-hand rule. And so you'll see in 1 minute why I am a physics teacher and not an artist or an art teacher. So So here we go. Here's your hand. Okay, so our fingers are kind of pointing upwards. They should be pointing upwards in the direction that these field lines are going. These field lines are all upwards, right? So our fingers are pointed up because the field lines are pointed up. And remember, the field lines point from north to south. That's why they're pointing upwards. So our fingers are up. Our thumb is pointing in the direction of the motion, of the movement. So this is the way that we're moving this piece of wire through the field lines. So the field lines are up. We're pulling this piece of wire this way through the field lines. And then we look at which way is our palm facing. Now we can see that our palm is facing in this direction, which means the current will go in this direction. So I think I have a better picture of this coming up here. Oh, no, sorry. This is just showing us that, yes, indeed, we were correct. The current is going in this direction. So again, that's just because, let me try and do this a little better this time. So again, fingers are pointed up. Our thumb is pointing in the direction that the wire is moving. And then the palm of our hand is facing in the direction that the current is going. So that's what that says right there. Okay, so now, how could we increase the size of the current that we're inducing here? So the thing is, if you move, like in this example, if we move a single piece of wire, like this is just, we are moving just, we can see that this is just one piece of wire here. So if we want to have more current flowing, what we need to do is have more pieces of wire. We want to have many pieces of wire. We want to have lots and lots and lots and lots and lots of pieces of wire that are cutting across these field lines. So one way of doing that is instead of using a straight piece of wire, we use instead of using a piece of wire, we use a coil of wire, like shown right here. And this is a whole coil of wire. And so now instead of just having one piece, so this coil, like this is a side view of that coil. So instead of moving a single piece of wire downward through cutting across these field lines, now we're moving a whole bunch of loops of wire. So each loop of wire in this loop, each loop counts as its own piece of wire. So this loop, it looks like it has tens, dozens, if not over 100 loops of wire. So it's as if we're moving 100 pieces of wire downwards all at the same time. So we have 100 pieces of wire cutting these field lines all at the same time. And that's going to multiply our current by 100 times if it is 100 loops of wire. Okay, so this, just to show you, this is just another example of how we can induce a current in a wire. So in this case, we can see we have a coil of wire here. This thing right here looks like a clock, but it's actually supposed to be an ammeter, which reads current. Or it could also be a super sensitive ammeter is also called a galvanometer. And a galvanometer is just an ammeter, but it's just super duper sensitive. So it can sense very small changes in current. So anyway, the point of this picture is to show you it doesn't matter whether you move the wire or you move the magnet, because in this case, we're moving the magnet through the wire. We're not moving the wire around the magnet. So the point is, it doesn't matter whether you move the wire or whether you move the magnet. The important thing is that they're moving relative to one another. Okay, so this whole thing, this is a bit of a summary here. This process of creating electricity is called electromagnetic induction. So that's what it will say in your syllabus. That's what it will say on exams. But I think it's easier to remember this as the generator effect. So this is, and it's easier to remember as the generator effect because what you're doing is you're generating electricity. And I find it much easier to remember by the generator effect as opposed to what we'll see later. So we'll look at the generator effect now, and then in a few weeks, we'll be looking at the motor effect, and we'll see that those two things are exactly opposite. So the whole thing with the generator effect is that the wires, it is wires cutting magnetic field lines. So anytime you have a wire that is cutting across magnetic field lines, you're going to have an EMF, which is induced in that wire. And if that wire is part of a complete circuit, you will get a current flowing. And that's just what this third point says. The induced EMF causes a current to flow if there is a complete circuit. And then this is what we already mentioned before. This is also called the generator effect because electricity is being generated. And again, this is how our electricity is generated. This is how all the electricity in your house is generated. It happens at some power generating station, and all they are using there are really, really big magnets, really, really big and many, many turns of wire, and they're using movement. And that movement can either be made from wind turbines, from burning coal to boil water to turn a turbine. In any way that electricity is generated, you always have to have something that gets a turbine turning that can then turn a generator to generate electricity. Okay, so now we come to probably the trickiest part of all this, and that is Lenz's law. And so basically, Lenz's law states this right here. The magnetic field of an induced current always opposes the magnetic field that created it. Now, what does that mean? Well, let's take a look at this first picture. So let's say here we are using this magnet. So we're going to be moving this magnet in this direction. So we're moving this magnet this way, which means, well, this magnet obviously has a magnetic field around it, which will look something like this. So as we move this magnet this way, this coil of wire right here is going to be cutting these field lines. As these field lines are moving through this coil of wire, we say is cutting those field lines. Okay, let's get rid of this here. Now, so Lenz's law, again, states the magnetic field of an induced current always opposes the magnetic field that created it. So in this case, the magnetic field that is creating the induced current is coming from here. So here's our magnet. And we can see this magnet is moving this way. So basically, we have a north pole that is moving this way, which means the current that gets induced in this coil will try to oppose the change that's making it. So it will set up a current. The current in this wire will be such that there is a north pole on this side, because this side is trying to oppose this change. What is the change that's creating the current? Well, the change that's creating it is this magnet. Oops. The changing magnetic field that is inducing the current here comes from this magnet moving in this direction. So we have a north pole moving to the right. So the current that gets set up in this wire will create its own magnetic field so that the north pole of it is facing the north pole of this, because it's trying to resist the change that's creating it. It's trying to stop this north from moving in by repelling it. So let's see another example of that. So what if instead of pushing the north inward, we were moving the north away to the left in this case. So again, you have to imagine there's a magnetic field around here that is cutting this coil of wire. So the magnetic field from this magnet is going through that coil of wire. So in this case, we're moving the magnet to the left. So the current that gets induced in this wire now, because of that changing magnetic field, because these coils are cutting field lines that is moving away from them. In this case, a north is moving away. So the current that is induced in this coil will be such that it will create a south pole at this end to try to stop this north from moving away. It's always trying to oppose the change that's creating it. So again, when the north's moving in, a north is created on this left side to try to oppose the change, being this moving magnet. This trying to oppose the change that creates it by making a north on this side to oppose this moving north. But if that north is moving away, it will create a current such that a south magnetic pole is created on this side to prevent this change that created it. That's kind of a complicated one, and we'll have to spend some more time on this, I think, later. So let's see what this sort of looks like. Here we have a magnet, and we have a coil of wire hooked up to a light bulb. And so let's just see what happens when we move this magnet. Oh, wow. If I move it away, so just notice one thing. So moving the magnet near, it doesn't even have to be in. Look, I'm out here and I'm still having an influence because the magnetic field of this magnet extends quite a long distance. So one thing I do want you to notice is that if I move this magnet to the right, did you see all of these electrons? Did you see them all move down? So I'll do that again. So if I move it to the right, well, maybe I'll try that again. Moving to the right, they all move down slightly. And you can see if I move it to the left, like this, they moved up. To the right, they move down. To the left, they move up. To the right, they move down. To the left, they move up. And it goes the same with the south side. If I move the south side away, they move up. If I move the south side towards it, they move down. Up, away, towards it, and down. And so just so we know, if I'm moving the south towards it, and that's inducing a current, that will induce a current such that there's a south magnetic pole on this side and a north magnetic pole on this side. Because if I'm moving the south towards it, it sets up a magnetic field that tries to oppose that change that created it. And one other thing we'll look at right here is the generator effect. And so this is essentially how all of our electricity is generated in our houses. So you have something that's causing a magnet to move. And you can just see, so now we have our magnet spinning. This is essentially like a little turbine. So this little turbine is spinning this generator. This whole thing makes up a generator. And you can see that from the point of view of this coil of wire, there's a north facing it, and then a south, and then a north, and then a south, and then a north, and then a south. And it keeps alternating. And that's why the electrons in this coil of wire are going up and then down, and then up and then down. And that's exactly why our electricity is AC. When you plug something into the wall, you're plugging it into, I believe it's 60 hertz AC. And that just means that the current that comes to our homes and businesses is alternating at 60 times per second because the magnets would be spinning at 60 times every second, which means these electrons in the wire are going to go down and up and down and up and down and up 60 times every second. So just remember, if this magnet is spinning at 60 hertz or 60 revolutions per second, these electrons will go down and up 60 times a second. And that's why the electricity in our homes is 60 hertz, because at the generating station where the electricity we use is generated, those magnets are spinning at 60 hertz or 60 times every second. Okay, now, now that brings us to an exam style question. So this is actually from a past paper. So what is it saying? It says figure 8.1 shows the bar magnet being inserted into a coil of wire. So we can see right here, this magnet is moving in this direction. The north pole and the south pole of the bar magnet are marked. We can clearly see that this, we can clearly see that this side is north and this side over here is south. Okay, and so the question is, So the coil is connected to a galvanometer. And again, remember, just a galvanometer is basically just a super sensitive ammeter. And hopefully we all remember that ammeters are used to measure current and voltmeters are used to measure voltage or EMF or potential difference. Those are all the same thing. So it says the coil is connected to a galvanometer. Explain why the galvanometer deflects as the bar magnet is being inserted into the coil. Well, why is this bar over here going to deflect one way or maybe the other way? Why is it going to deflect? Because we have the changing, or instead of saying changing magnetic field, we should probably just say a moving magnetic field. So, well, actually, let's make it even simpler. We'll just say the magnetic field, and just for mentioning magnetic field, you already get 1 out of 3 marks. The magnetic field from, or the magnetic field of the magnetic field of the magnet is moving. So there's 1. The coil of wire there is cutting the field lines. So the coil of wire is cutting these magnetic field lines that are around this magnet because the magnet is moving in. And essentially this, anytime you have a wire, especially that is connected to a complete circuit, a wire cutting across magnetic field lines, this we'd say, we'd say this induces an EMF in the coil. And remember, an EMF is just the same thing as a voltage, but it is the same thing as a voltage for a supplier of energy, as opposed to saying potential difference, which is when something is using energy. So that is it. The magnetic field of the magnet is moving, the coil is cutting the field lines, and this induces an EMF in the coil, and therefore the galvanometer. And this induced, well, maybe we should say this induced EMF, the induced EMF induces a current, because this is a galvanometer, which is a sensitive ammeter, which reads current, not potential not voltage. So this induces an EMF in the coil, and then we might just add which creates a current. And then the second part of the question, explain what determines the direction of the reading of the galvanometer. So what determines whether it deflects one way or whether it deflects the other way? Well, what determines that is basically the movement of this magnet, and it depends on which pole is facing. So in this case, so explain what determines that. It is determined by the direction that the magnet is moving. And we can say specifically in this case, because we have a north pole coming into it this way, that means that the current in this wire is going to be such that it creates a north pole on this side and a south pole on this side. So we could even say that, and that could get us another mark. We could say a north pole would be on the left side of the coil. and that would be enough. And that is really it for the generator effect, or for electromagnetic induction. Let's see here. Where are we? Yes. So hopefully that made some sense. I know it's a little tricky. You might want to have a look in the book to make sure you completely understand things, especially the right-hand rule, and especially Lenz's law. So I will assign some multi-choice questions and some structured questions so you can get some practice with this. And then I'll assign that on Google Classroom. If you have any questions about this, or if something didn't make sense, someone send me an email, and I will just maybe I'll make another video to clarify anything that wasn't clear enough in this one. Okay, so I look forward to hearing from you, and good luck with the upcoming week.